Hello, in this video I'm going to cover pointers, which is one of the difficult topics in C++. So hopefully you'll find this video lecture useful to understand pointers. So we'll cover some background information first before we covering pointers. This is a reasonably generic slide. Any program in most modern OSs, it's Windows or Unix or any operating system, typically we expect to see several types of memories to be used. Okay, so here I have kind of mentioned 4 types of memory. These are all logical segments, logical memory parts of the program. So first is the code memory. So code memory is where the executable code is stored. So this contains the executable code. So whatever we compile and when it's ready to run, whether it's .exe in Windows or in Unix a.out or something like that, it's executable code. This is typically read-only code. In the old days, hardware did not provide lot of protection, so we couldn't make a portion of the memory as the read-only. So during the runtime, even the code itself can be changed, so which is kind of scary. So nowadays, all the hardware has matured and processors have the capability to kind of indicate particular memory is completely read-only. So when a program is running, that code, corresponding executable code, remains as read-only. Okay. That not only helps us with the protection, it also enables when multiple programs are running, same program, multiple instances of running, it manages to use the same code for all the programs, okay, all the instances of that same program. Okay, that's not probably very important at this point. Okay, let's move on to the data memory. Data memory, what I mean by data memory is pretty much the global variables. Okay, so primarily data memory is used for global variables. Okay, obviously it's a read and write, because anytime data is involved, it needs to be read and write. If you don't have any global variables, obviously this data memory may not be much at all, it may not exist, but I have a feeling most operating systems runtime environment, it does have some global variables, even though user may not have defined it. Okay, the next one is the stack memory. Stack memory is quite interesting. It has local variables, right? The stack is used for all the local variables inside a function or a method. Whenever you define local variables, so the stack contains them. Also the runtime tracking, meaning which method you are in. When you invoke another method, we push the current address in the current method, so that you can come back after finishing the invoked method, come back and run it again. So really stack memory contains local variables and also the method invocations and returns, and all that time it's utilized to keep track of where you were. So for a runtime kind of for program to run properly and jump around between invoking, return of methods, stack memory is very, very important. So that is also known as a stack frame, I believe. Stack frame is the term used to kind of capture when you invoke a method, you have to pass in the parameters and store the current current address, and the invoked method has to define the local variable. All those things together is called as the stack frame. Okay. Again, in this lecture, we are not going to focus too much on stack frame. We are just going to talk about variables and how the memory is used to access the variables. That's what we'll be focusing on. Last one is the heap memory. Heap memory is pretty much used for dynamic memory allocation, right? So heap automatically means is dynamic memory allocation. Dynamically allocated memory, which means in your program, if you don't do the dynamic memory allocation, obviously you're not going to use the heap. At least the program doesn't, user's code doesn't use. Who knows, in a programming environment, there may be something in the runtime environment may use some heap. But typically, I have seen in Unix, for example, if you don't allocate a memory, a few tools are there to display how much memory, heap memory we use. It shows that heap memory usage is 0. So it's most of it should be the user behavior, okay, what user's code does. Going forward though, we'll be mostly focusing on stack memory and heap memory, okay. I guess that's because of the way current programming is done. We kind of stay away from global variables, more and more local variables we use, and more dynamic memory we use, okay. So that's why we kind of focus on these two type of memories. So before we go too much further, even though this is not directly important topic, relevant topic for pointers, I thought it's kind of good to point it out. So what does it mean to say something is a 32-bit computer versus the 64-bit computer? For that we have to cover another basics. Is all the memory in the computer is byte addressable memory. So this is kind of indicates 1 byte. So when we say byte addressable memory, so each byte can be addressed, right? Each byte in the main memory can be addressed. So if this is the top, you typically say, this may not be the top, right? So let's assume it's kind of in between. So typically this is the hexadecimal memory we assume. If it reaches the top, the address is going to be 0, 1, 2, 3, 4, so on, okay? Like this it keeps going, so if you use the hexadecimal, it's going to be 0xa, that's a fancy way of writing 10, right? So more memory you have, the more this addressing, this index has to go very big, right? So typically nowadays our computer memory is 2 GB or 4 GB, so on, right? 2 GB or even 4 GB memory. So what does that mean? Well, 2 GB means if you do some math computation, it's let's see, there's basically 1 kilobyte and megabyte and gigabyte, right? Remember the kilobyte, let's write down something here. Kilobyte is 2 power 10 bytes, okay? Gigabytes is 2 power 20 bytes. Megabytes, sorry, and gigabytes is 2 power 30 bytes, right? So you can see it's going up by 10 because MB is nothing but kilobyte into kilo, basically, right? 1024 into 1024. Gigabyte is 1024 into 1024 into 1024. Remember, the 2 power 10 is 1024. So everything in computer is 2 power. Okay, that's because of the way the memory is organized, the hardware is organized, okay, by addressing. So when with a fixed number of bytes addressing, it always end up as the 2 power so many bytes. Anyway, so when you say 2 GB, you can see it's a 1 GB was 2 power 30 bytes. So this is 2 power 31 bytes, right? So that's a 2 GB. 4 GB is 2 power 32 bytes. Okay. So if 2 power 32 bytes of memory you have, main memory you have, so you can see that it's 2 power 32. That's a lot of addressable locations, right? So this indicates that the address bits, you need the 32 bits. Okay, to access this 2 power 32 bytes, we need 32 bits. Yeah, 32 bits of memory. Again, you can do a simple math, to why this is the case. So I'm not going to delve too much into that. So the bottom line is, more memory you have, more number of bits, address bits you need. Okay, so lot of address bits means that your address will be very long too. Okay, that's a one side. But again, question is back to this 32 bit. Is there any relation between this 32 bit address bits versus 32 bit versus 64 bit computer? Not really. This 32 bit 64 bit, what it's talking about is the data bus size. Okay, this is a data bus size. Okay, data bus width or size or something like that you want to data bus size. In other words, parallelly how much memory you can access. So here you see the two more diagrams here, right? So you have this 4 bytes, first 4 bytes. This 4 bytes is kind of written like this. See, so this is index 0, maybe index I should write inside, index 1, index 2, index 3, so on. Okay, index 4, index 5, index 6, index 7. So what does this mean? Well, what this means is that when you give your address 0, computer not only can give 1 byte, it can actually give 4 bytes. Why is that? Because the data bus size is 32 bits. So whenever your address is given, whenever your address is specified, it can give that whole 32 bits, whole 4 bytes of data it can give. So that's very powerful operation, because remember, for example, integer, it takes 4 bytes. With one memory access, you can get all 4 bytes. What if there are one double, let's say? Double typically occupies 8 bytes, right? So let's say this is double, that's 8 bytes. So to access the 8 byte in a 32-bit computer, it requires 2 memory accesses. You need one memory access here and one memory access here. Okay, so 2 words. This is, by the way, said as a word size. Okay, word size is 32-bit here, whereas this word size is 64 bits. Same double, right? Same double there. It may be with this memory address, you can access the whole 8 bytes in single memory access. So you get the 8 bytes of data together with the one memory access. So you can see how fast it can be. So every time with the one address access, you can get multiple bytes. So in the 32-bit computer, you get 4 bytes. 64-bit computer, you get 8 bytes. So theoretically speaking, 64-bit machine can run twice as fast as 32-bit. Theoretically speaking, okay, the maximum. Well, most of the time you are accessing integers or something small, so really 64-bit machine will not make a big difference, right? So you can see the double or any complex variables, you can see that it can potentially make a big difference. Okay, very good. So that's a kind of insight into 32-bit versus 64-bit computer. Again, it's not extremely relevant to what we are going to talk about. Okay, I thought it's just a side note. I want to mention that to you. Okay, now let's dig deep into the memory, how the memory is being utilized or allocated when for the programs. Okay, so here we are going to assume this is main. I know I haven't mentioned it here. So this is within the main. You have these two variables, integer x and array of 10. So I have shown here stack memory and heap memory. Where do these variables go is the question. So where are these variables? Memory, where is it allocated? You can see these are really local variables for the main. So they are going to be local variables, right? Local variables are in the stack memory. So it's going to be 4 bytes of memory typically. Okay, and that is for x. Then you have array 10 integers, right? 0, 1, 2, so on. Okay, so you can see that I'm kind of loosely using this memory, kind of assuming as if the width is 4 bytes, all that. Okay, again, I'm just going to talk it a little bit high level in logically. I'm not too worried about exactly how many number of bytes or anything. Okay, so internally this is how it's going to look. So index is going to be 0, 1. This is a array index. Okay, not the memory address. I'm not talking about memory address. Okay, so final one is the 9. So if you look at x and array, everything is allocated in the stack memory here. Okay, pretty simple here. Okay, so let's slowly start getting into pointers. So again same code. I'm not going to write main every time. So x here, we have x as the integer. Then we have something called star xp. Star xp means xp is a pointer. Okay, xp is a pointer. It's going to point to a memory location that contains a integer. Okay, that's what it means. Int star xp means, see, we need to always understand how in plain English you can say something. Okay, int x means x is a integer variable. Int star xp means xp is a pointer, or it contains a address inside, right? It contains a address and it points to a variable, points to a memory location that contains a integer. That's how you should read it, because it's int space star xp. See, the data type for x is integer, star xp is integer. See, so let's see. Let's make this little bit clear. I'm going to erase this thing and rewrite it. And let's say this is x and this is xp, and let's say x is the address is, I'm just going to come up with the address 1A5B. Good address? I hope so. I think B is 11, isn't it? So C is better address, I think. I'm just talking about a word aligned address. So C, D, E, F. Okay, so then that's let's say hex 1A5C. Okay, and then this is next address. If assuming it's below that, it may be 1A60. Okay, so now xp is pointing to address of x. See, that's how again you read this. xp equal to address of x. This both statements or both mechanisms are same. This mechanism versus writing this way, both are exactly same. Okay, here we are declaring the variables, defining the variables and initializing directly in the same line. Here we are initializing in the next line. That's the only difference. Okay, so both are very much acceptable methods. So here what happens is that xp is equal to address of x. So inside this, xp is assigned address of x. Okay, so what does this mean? Well, this address is pointing to xp, pointing to x, I'm sorry. So the xp is Cassia address, and that is the address of x. Okay. Okay, so how can you allocate value to x at this point? At this point, how can we allocate value to x? Well, you can just say x equal to 50. So as soon as you do x equal to 50, it's going to store there like that, right? Then you can write star xp equal to, well, this one and this one both do the same thing. Okay, so if you do x equal to 50, wherever x's address is into that memory location, I know I'm writing in decimal. In reality, it's going to be hexadecimal and all that, but we are just keeping it high level. Star xp means wherever xp is pointing to. See, xp is a pointer variable. So you look inside, there's a address. Wherever it is pointing to, change that memory location to the corresponding value. Okay, so this is an alternate way of kind of a little bit roundabout way of allocating, assigning a value to a memory. Okay, let's keep going. Okay, so let's go back there. So far we haven't used the heap memory at all, right? So now finally we are getting there. Now we are talking about just xp. That's a address. And what we are saying is that xp, we are going to, it's only the address. There's no integer variable here, only the address. And we are doing new integer. I want one integer, memory for one integer. Okay, we are dynamically allocating memory for one integer. So now, so let's say this address is something. Purposely I'm writing small addresses. In reality, address can be very long, typically 4 bytes long, which is double of this. Okay, so this will be, if that's the address we get allocated, so this address will be here and it will be pointing here. So now when you do right here star xp equal to 50, so we take this address and wherever it's pointing to, and you assign 50. And this is the first time we are allocating memory in the heap. Also, another thing, interesting thing about this is that there is no variable name for where the 50 is stored. See, there is no direct variable name for where the value 50 is stored. If you look back on the previous page, there is an integer x which was in the local variable, and we were storing it. So that's why we were saying you can write like x equal to 50 or star xp equal to 50, right? So whereas here it's not local variable anymore. xp is pointing to a dynamic memory location. Okay, xp is local. Okay, but the integer itself is in the heap memory. Okay, one rule in C++ is that since there is no automatic garbage collection, if you allocate, you have to clean it up. Okay, so since we allocated here, memory, we have to, when the program ends, before that's good practice to delete that memory. Okay. So for a small program, C++ program, you may not care the one they run over a few seconds, because when the program ends, the OS will reclaim all the memory anyway. Okay. But if the program is going to run forever, like a game engine, it may run for a long time, if not forever. Our best example is the web server. Okay, the web server is something that's going to run forever. We expect it to run forever. Then particular function, remember, this need not be main, it can be something else, right? So if some function gets invoked, it allocates dynamic memory, and when it's done, it should release that memory. Okay, otherwise over time we keep on, if you forget this, let's say we forget this one, then over time, whenever this method gets invoked, you keep on allocating memory, so the heap will be, at some point, all the heap will be consumed. Okay. So at that point, you start to run out of memory. Okay. So that's why this delete XP is very important. Okay. If you allocate using new, you should delete the equivalent one. Okay. Let's move on to the next slide. Very similar. XP, memory address, pointer. It says allocate me a integer array of 10 items. 10 integers. 3, 4, so on. Okay. So that's the index, not the address, it's a index. Right. So now the XP is pointing to that address. So whatever the address of that is, what the address of this newly allocated memory is, what we have in XP. Okay. So look at this notation. Notation is little bit different. The previous one was just we allocated one integer, then when you deleted, you just said delete XP. So what does this mean? Well, delete the memory address, delete the memory allocation pointed by XP. Okay. And whereas here we did allocate an array of 10 items, and when you delete, we say that delete the array pointed by the XP. Okay, so we do make a distinction there, whether XP is pointing at an array or the individual item. Okay, at least in this delete line. Okay, so how do we access particular value, particular item in the array? Well, this is like just like a regular array. You know, at this point, now that's the amazing thing about these pointers, is that makes it so easy to use. You know, at this point, XP works like just like a array. Okay, so you can say XP of 4 equal to 100. XP of 4 equal to 100. XP, whatever address it's pointing to, fourth location, it's going to be 100. Okay, so as simple as that. It's just like a regular array. Okay, so just that this happens to be dynamic array because of we are using new and all that stuff. Okay. In fact, this is one of the thing I wish C++ we didn't need to distinguish, because what if the programmer makes a mistake? Instead of this, what if the programmer writes just delete XP? You know, believe it or not, it can create problem in C++, unfortunately. Okay, so you have to be careful how we do the delete. It should match with what we did in the allocation. Okay, so let's look into this some more. Here's an interesting notation. That's right, there is a array, but then we are saying *2. Okay, so how does it look like? Well, it is a array. XP is a array. Zero, 1, 2, 3, 4. Okay, so there's a 5-item array and all of them are pointers. See, so you have the array XP of 5 and the type is integer star. See, okay, so that's how you kind of read it. So each one is a pointer. Okay, we have a pointer array and we have this loop here, and we are allocating array of 10 within this loop, right? And you are assigning to XP of 0, then XP of 1, XP of 2, so on. Okay, so this every time when you do this new int 10, it returns a pointer, it returns a memory address, right? So memory address of that new allocation, right? So let's see, one memory allocation. So 5 blocks of memory. Okay, 5 blocks of memory allocated, and each one is a 10-item integer array, dynamic memory allocation, and we have these pointers all set up in the XP array, and you can use. So this is almost like a 2-dimensional array, right? So you can how do we access, or when we write XP of 2, what does that mean? Well, XP of 2 means this pointer, right? XP of 2. So what does it mean to say XP of 2 of 5? Well, XP of 2 is XP of 0, XP of 1, XP of 2. You go through that, and item number 5, index 5. Okay, so that's the item we are talking about. Okay, because you kind of go from here and go through there, and then use the second index. Okay, so if you assign this to some value, that's the value that will get updated. Okay, so how do we delete now, since we allocated 5 memory blocks? Well, you do the same for loop and delete that, right? So we allocated, and let's see whether we have the next slide. No. Okay, so we allocated, use the same for loop, delete array pointed by XP of 5. Okay, delete the array pointed by XP of 5. Okay, so that's how you delete the individual arrays. There are 5 arrays, right? That's why. Okay, so when you look at a pointer which has the address, does it tell you whether it is pointing to one item or an array of items? So for that, you have to look into this code. See, the sample code 3 says a pointer pointing to one integer there, right? And here, same pointer, basically we wrote using the same pointer, we wrote this code, is now it's pointing to array of 10 integers. So right in between, just by looking at XP, can we tell whether it's pointing to one integer versus 10 integers, 100 integers, so on? Unfortunately not, right? So it's just a pointer. We have no clue how many items it's pointing to. Okay, so that's one of the challenges actually, since a pointer doesn't tell how many items it's pointing to. Sometimes people kind of write code and it goes outside the boundary of the valid memory sometimes. Okay, so let's look into the pointer arithmetic. We know when xp is a pointer, you can write xp of I to access the ith item in the pointer, right? Ith item in the array. Sorry, I'm a little bit sleepy. Yeah, so let's see, xp dynamic memory allocation, like that, it's pointing to. Okay, so now when you say xp of I means that ith index. Okay, so let's say this is I, let's say. Okay, so when you say xp of I, it means it refers to this value. So it refers to the item in this index. Okay, xp of I. Then when you say address of xp of I, and that is this memory address location, right? So address of xp of I, where it xp of I the value appears, address of that. Okay, you have some few other notations, xp plus I, you can write it as xp plus I, and other point, so that's equivalent to this, and more interestingly, you can write xp plus plus, xp plus equal to 2 and all that. Okay, what does that all mean? Well, xp is pointing to an integer here. Remember, it's just a pointing to an integer array. When you write as xp plus plus, we know this notation in integers, right? When you do plus plus, you move to the next value in integer. Similarly, you add 2 to integer, so on. So, but how does that make sense to increment a pointer? Should it point to the next byte? Remember, here we have been dealing with integer examples. If you simply point to the next byte, you are basically stepping into the integer, so I don't think we want that, right? So pointer arithmetic is one of the kind of smart ways to manipulate the arrays. When you do xp plus plus, it actually address goes up by 4 bytes. Okay, so let's see. Initially, let's say the address is 15A0. Okay, when you do xp plus plus, so this is the 15A0 address, and next one is 15A4, right? Because of 4 bytes of integers, so this is 15A1, A2, so on. So there are, each word is 4 bytes. Okay, so when you do xp plus plus, at this point 15A0, once you do increment, it becomes 15A4. Okay, so because xp is pointing to an integer, integer requires 4 bytes to store one data, right? So when you do plus plus, what we are saying is we are making the pointer point to the next item. Okay, not the next byte, it's the next item in the array. Okay, that's why it becomes 15A4 xp value. So when you do xp plus plus, what really happens here, right, is xp equal to xp plus plus pointed items size. So here pointed item is an integer. Integer's size is 4 bytes, so xp equal to xp plus 4. That's what it happens. So what happens here then? Xp plus equal to 2. So this is equivalent to xp plus equal to 1, right? Xp plus plus is nothing but xp equal to xp plus 1. So this one is kind of you can write, there are several ways to write, right? Xp plus equal to 1 also you can write. So this is the xp plus equal to 2. So you want to go up by 2 positions. So which means xp, it will result in as xp equal to xp plus 2 into published the pointed item size. Okay. So the corresponding address will become 15A8 and 15A B, that's C, I think. C is the 12, right? 4 plus 8 equal to 12. So 15AC. After adding 2. Point arithmetic are one of the confusing ones. So kind of take it slowly, and hopefully we'll cover few more examples later. Okay, so let's get back into our code again. Now that we understand the pointers reasonably well, now we are ready to do the double stars. Okay, let's see what this is. XPP, XPP is a double star. We come to that soon, don't worry. XP single star, that's something we know. X is here. XP equal to address of X here, right? XP equal to address of X, which means we are going to point to this X, right? So then XPP equal to address of XP. So this guy is going to point to here. So if the address of XP is 15A0, this one is 15A4, 15A8. So inside you have 15A8. Inside here you have 15A4. XPP is pointing to XP and XP is pointing to X. Okay, that's what this double star means. I have a pointer and it contains an address of a pointer to int. Okay, so it's a more redirections basically. So from here XPP, to access the integer you have to kind of do 2 steps. Okay, whereas from XP you can directly go to, using the address you can directly go and access it. So here is another way. They write at this point. There are several ways you can write this thing. X equal to 50. Okay, so that will fill in 50, or star XP equal to 50. Wherever XP is pointing to, pointer pointing to, assign 50. Or you can write as XPP star XPP equal to 50. Okay, star XPP means 1 redirection, star XPP means 2 redirections. Okay, it's kind of useful. Double star XPP is to kind of build a dynamic 2-dimensional arrays type of ones. Okay, it's not as popular of the single star. Okay, so okay. Not very different, to be honest. Let's see, xpp here. xp next one, array what are we saying? xp equal to array. See, did you see something interesting? Till now we used to say xp equal to address of x, but once it comes to arrays, array name alone is the address by itself. Okay, indicates the address. So you don't need to say address of array, rather you can do xp equal to array itself. However, there are equivalent ones. Either you can write like that, or you can write xp equal to address of array of 0. Both are the same thing. Okay. Either way, xp will be pointing to the first item, and then xpp equal to address of x, address of xp, xpp equal to address of xp, so it's pointing to xp. Okay. Okay. Okay, another similar one, just that there are a few more arrays. xpp here, and xp is the array by itself, right? Then array of 10 is the array, and how we write is xp equal to array, and I believe that's incorrect. It has to say xp is 0 equal to array, and okay, yeah, so xp of 0 equal to array, makes it point like that. So then xpp equal to xp, it points like that. Okay, this is really partial one, because you didn't even allocate the remaining ones and all that. So okay, let's look into some more dynamic two-dimensional array. So here you have only one variable in the stack, which is xpp. Okay, so then we are saying we want new 5 integer stars. Okay, so we want to allocate an array of 5 pointers. So you can see the pointer array also has moved in. See, the previous example pointer array was in the kind of in the stack, right? So we are playing with the pointer array in the stack. So this is the first time we have managed to move the pointer array itself to this the heap. Okay, so now for each one you are allocating 10, so that's no difference. Okay, so that's how the corresponding code looks. So each one is a 10 integer array, and we allocate and we update this xpp of I each location to this new memory block. Okay, we allocated fully dynamic two-dimensional array in the previous slide. So how do we clean it up? So how we clean it up is we allocated this first, then we allocated this. So the latest allocation will go out first, right? Because if you deallocate this, then you kind of lose track of these guys, and how will you deallocate? Okay, so first you have to delete this stuff first. The end, the 10 integer arrays in the end of the chain first, then you can delete this pointer array. That's exactly what we need to do. So for same loop and delete array pointed by xp of I. After doing that, finally do delete array pointed by xpp itself. Does this make sense? See, delete this, delete this, delete this, delete this, delete this, and then delete this. Okay, and return back. Okay. So I will stop this lecture. This is the kind of introductory portion with the integers and pointers. We are playing with that. So I'll let it kind of sink in, and I'll do the advanced pointer version very soon and post it as well. Okay, thank you.